as one of two major reaction types. And a lot of reactions are acid-base, proton transfer. That's why we spent so much time talking about, you know, acid-base chemistry, is it's such a fundamental, it cuts across a lot of chemical reactions that you'll be exposed to. And then the other type of reaction is an oxidation reduction reaction, a redox reaction, and these are electron transfer reactions between species, you know, that would be in solution. Okay. The other way to think about oxidation reduction is with an electrode, right? So you can transfer electrons from molecule to molecule, but you can also use an electrode to transfer electrons, and that is the basis of how we use electrochemistry. It's so immensely used today. You know, think about the Tesla car, you know, the cell phone, everything uses electrochemistry in the galvanic cell that we refer to as a battery, right? A battery is just a big electrochemical cell. Okay, so electrochemistry deals with chemical reactions that produce electricity. These reactions involve the transfer of electrons from one species to another, and they are referred to as oxidation reduction reactions. And what you're looking at is a lithium-ion battery schematic. But fundamentally, the electrochemistry is based on, again, on the passage of current. And the current, does anyone know what an amp stands for? An ampere or an amp in physics, I don't know if you've had physics or not, but an amp is a coulomb per second. And so the coulomb is a unit of charge, and the passage of charges through solution or through a wire is related to the passage of coulombs. And the number of coulombs that pass every unit of time, every second, is referred to as an ampere. Okay, a coulomb has a very small charge for a proton, and then of course the same and equal but opposite charge would be for an electron. Okay, so an electron would have a minus 1.6 times 10 to the minus 19th coulombs with a minus sign in front of it, but the charge is the same in an absolute sense. Current is the rate of flow. The unit, again, is an amp, which is a coulomb per second. Electrical potential is the ability of an electric field to do work on a charge. So voltage or potential is a unit of potential energy, right? It's not kinetic energy, it's potential energy. It's stored energy, and it's stored the electrochemical unit of energy storage is the voltage, okay? And the way you can think about electrochemistry or more generally electricity is the flow of amps or coulombs, right? Elementary charges that are quantified in this amp, coulombs per second, flowing through a constriction, and the constriction is an ohm. I'm sorry, the constriction is a resistor, okay? And the resistor has a resistance to current flow associated with it, and the resistor unit of measure is ohms. So higher ohms mean more resistance, and in order to get current or amps to go through higher and higher resistances, we have to get our buddy here to apply more and more kick, right? More and more voltage. So V is equal to IR is the one of the fundamental relationships in basic electricity studies. And when you get to physics, you will study that a lot. Dr. Pearson, I think, teaches that. Current is the amount of electrons that is being passed in coulombs per second, as we've said before. Voltage, potential energy, and then the ohm is a unit of resistance. So this graphic, this cartoon, I think is a very useful way to think about V is equal to IR, okay? All right, if there are no questions on that, we will move right along here. So oxidation reduction reactions. Oxidation is the loss of electrons. Reduction is the gaining of electrons, okay? And this is a little way that one can use to think about it or to remember it. Leo the lion goes grr, right? Lose electrons through oxidation. Leo, gain electrons through reduction. Grr. Okay. And this is another one. Oxidation is loss, reduction is gain. Okay, oil rig. Okay, so far so good. It's probably the first significant concept is just to remember, you know, where what oxidation reduction is. And that is simplified, an oxidation or a reduction oxidation process is often termed a redox process. Okay. There's a lot of detail here, but you'll, of course, we'll make this available to everyone, but kind of in a nutshell, electrochemical reactions are a chemical reaction involving the transfer of electrons, occur between an oxidant and a reductant, or simultaneously you can get electrochemistry between inner electrode surfaces and oxidants or reductants. I probably should have said that here. Referred to as redox reactions, can harness voltage and move electrons. Electrochemical cells can produce energy. We mentioned the battery. That is another term for a galvanic cell. Galvanic produces energy. It's a way to store charge. Storing, we can store, and it's probably not the best term to use store here, but we can work, we could perform work within an electrochemical cell by applying voltage. And that's the opposite of galvanic, is an electrolytic effect where you actually physically plug your cell into a 110, so to speak, and you cause the electrons to go uphill, to go the other way. You cause an oxidation to occur where maybe it did not want to occur, or a reduction was occurring. You cause an oxidation to occur. That's an electrolytic cell, okay? So galvanic cells and electrolytic cells. Electrochemical cells are used to perform synthesis using electrons and voltage. One of the most common synthetic bulk or industrial processes is in chlorine production. Chlorine, essentially the production of CO2 gas is through the oxidation of sodium chlorides, chloride salts, or seawater salts. Okay. Current is a kinetic quantity. Voltage is thermodynamic, is stored energy. Current is kinetic, okay? Kinetics versus thermodynamics all over again, and it's all embodied within electrochemical processes. Current can quantitatively help you determine moles of substances. We will see that in a few slides. You can use current measurements to quantify material quantities, okay? Now we're going to get to the sort of the nuts and bolts of electrochemistry. And the first concept I want to talk to you about is referred to as a half-cell reaction. So the battery that we showed you is composed of two electrodes, right? There was a lithium electrode and a graphite electrode, and then an intervening a medium, right, into which those two electrodes were immersed, okay? And those two electrodes are responsible for two half reactions, okay? We're going to study them in half at a time, so to speak. And that's very useful to help us do that, to kind of think about electrochemistry. But in reality, you cannot do electrochemistry with one electrode. You have to have a complete circuit. Just like a circuit in your home has to be completed, and if you break the wire, you know what happens. You know, the current doesn't flow, right? If you have a line go down and all of a sudden your power gets lost to the house. Well, it's the same thing in electrochemistry. You really have to have a complete circuit in order to do electrochemistry. But having said that, it's very useful to think about these half cells independently, okay? And we're going to talk about the one on the left is silver, okay? And the one on the right is tin. All right, so let me ask you guys, somebody give me an answer here. What on the one on the left, what is being reduced?
The AG.
AG plus is being reduced. It's going to AG0, isn't it? So you've got a silver ion in solution, and that silver ion is being reduced by an electron. And then same thing on the right here. We also have SN, which is 10, 2 plus. It's being reduced to 10-0. Both cases being reduced to their corresponding metals. On the left, all you need is one electron. On the right, you need two, right? Because 10 in its one of its more naturally occurring states, 10 ion exists in the +2 state. That's its stable state. So the valence electrons of 2 plus are stable, relatively stable in solution at least, okay? And so that takes 2 electrons. So let me question here. If I was going to take silver metal, and let's just say well, actually the better one would be if I was going to take tin metal and I was going to reduce silver ion, how many silver ions would I reduce for every tin metal atom? Well, yeah, exactly. That's exactly right. You're going to reduce 2 silver ions for every 10 metal ion or atom, okay? And that gets to the fact that this is a very quantitative endeavor here, okay? Let's consider electrodes in solution now, okay? Now, I want you to, because I have a little typo. That 10-2 is not there. It shouldn't be there. But in any respect, what I wanted to show you here is that we have 2 silver metal electrodes in solution. Just in a solution of, say, you know, maybe just water, or maybe it could have salt in it, right? Now, if I have 2, and again, disregard the 10, that's that's a typo. If I put those 2 electrodes in solution, just in solution by themselves, and there's nothing else in the solution but maybe inert electrolyte that's not electroactive. So what I mean by that is something like, oh, you know, sodium nitrate or something that is not very electrochemically responsive or reactive. Any idea what the voltage difference between those 2 electrodes would be? And again, neglect the 10-2 ion. That's my problem. Anybody hazard a guess?
I would think it'd be 0.
Your thinking is exactly right. It is 0. There's no driving force, is there? Now, you know, just let me elaborate a little bit on here. Let me get my little pen. And so, you know, so again, this is a sea of electrolyte, and we probably got sodium plus ions in here, and what did I say, nitrate ions floating around. But you know, silver, if I have silver 0, these guys are not going to do anything. They're not going to react with that electrode surface, okay? They're not going to react at all. Now, the other point I guess I should bring is if I have silver nitrate in solution, this is a conductive solution, is it not? Do you know what I mean by conductive? The ability to carry or conduct current. That's a conductive solution from the standpoint that we have ions in it, right? It's a conductive solution. So theoretically, you know, at least in theory, we could have current, we could have electrons flowing there, but we don't, because those are absolutely identical electrodes, and Nathaniel was right. There is zero driving force to create a current, okay? And so that's a good sort of way to think about where one might start thinking about electrochemistry, okay? Really not getting any voltage or any current flowing in a situation like that. All right, so now let me ask you this, and again, please ignore my tin ion, that's not there. Now let's say we put some silver ions in solution, okay? And we still have our friends here. I'm gonna say sodium and nitrate. Again, they're just passive ions. They're just there to move charge through liquid. That's all they're there for. They don't do any electrochemistry. That's what we call an electrolyte. Okay, so they're just electrolytes. So now I've got a silver plus ion against a silver 0 electrode. And now, and I'm going to answer this question, there is some electrochemistry that can occur. You guys remember that reaction I showed you a couple of slides ago? Silver plus 1 electron going to silver 0. Well, in fact, that can happen, okay? That silver ion there can attack, and will, it will diffuse up to the surface of that silver metal electrode, and that silver plus 1 will go to silver 0. It'll go to silver 0. And of course, it'll stay there. It'll plate out right on that electrode. Okay. And similarly, we've got silver 0 in here. Well, the silver 0 is going to see that silver plus 1 ion, and it's going to go to silver plus 1. Okay. So you got silver plus 1 coming out over here, but you got, you know, silver 0 going back in here. So can I convince you based on that argument that we do have electron flow between that solution and that electrode? And in fact, we do have electron flow here. Does anyone disagree with that based on this discussion?
No.
Okay, that's clear then. Good, thank you. All right, now I'm going to ask you again, however, what is the voltage of that solution going to be? What is the voltage difference between those two electrodes, if any?
Can still be 0 or at least negligible.
You're exactly right, Nathaniel. You're on the money here. You're thinking exactly the right way. The voltage is still 0, guys, but the electron transfer reactions are now occurring, okay? So you still have what we've referred to in kinetics and thermodynamics as a dynamic equilibrium situation, okay? A dynamic equilibrium, okay? Still stuff is happening, just like in the previous chemical kinetics or chemical thermodynamics chapters we've had. It's just that there's no network is being created for us, is there?
So what, okay, so it's not, or well, it's still 0. What would make it not 0?
Thank you. That's the next one. That's the right way to think about that, Connor, and we're going to talk about that. So let me see if I can pull this. Let's add to what Connor just asked, because that's a wonderful lead into what we need to talk about next. Now we've got, I don't know why, good. So now we've got a little more complicated solution. All right, we've instead of having two, well, let me go back, shoot. All right, and instead of having two silver electrodes, now we have one silver electrode and one tin electrode. Okay, and we still have our electrolyte solution. You know, we still have this inert electrolyte, Na plus, and NO negative. So we still have a conductive solution. And now we've added, in addition to our silver ions, at some time t equals 0, let's just think initially, we added, so we have a silver electrode and a tin electrode, and we put silver ions in there, and at t equals 0, we also put tin ions in there. All right, so, and Connor, I'm going to go ahead and answer the question now that you've posed, and I think you probably know the answer to this, but now I would argue that we have at least potentially created a scenario where current can flow and where voltage can be produced, okay?
Is that because we added something else?
That's exactly right. That's exactly right. We have added, so we started out having something that has associated with it a thermodynamic voltage, and I'm just going to call this E0 AG. All right. And now we've done two things. We've added a tin electrode, which has associated with it an E0. Let's call it SN. And we now have two complete couples. We have the opportunity for tin to interchange with its tin cation, right? And so you get actual electron transfer here, right? And now you've got silver, and it's doing its thing with its silver ion electron transfer here. But I would argue, guys, that, and ladies, that if there is a difference between this E0 and that E0, then would we not see a difference in our voltage? And the answer is absolutely you would, Connor, just like you said. We've created a difference because we've created dissimilarity between the two. And let me show you something else. So what I would like to show you is that if we were also, well, yeah, we can do this with voltage actually. If we measure voltage versus time, okay, V versus time, and when we initially put that 10 ion in our at t equals 0 in there, you're going to get some voltage. Okay, now let's not talk about the quantitative. We'll quantify that in a minute. But quantitatively, you're going to have a voltage that's going to start out, I would think, but it's not going to slowly go down. Now, the reason it's going to go down, and this is getting into the detail, but I wanted to share it with you. The reason it's going to go down is because, you know, the tin is going to react with its guy and create a voltage and an electron transfer. The silver and the silver ion are going to react according to its half reaction, right? But the other thing that's going to happen is the silver plus and the tin 2 plus are going to react in solution. And because they're going to react in solution, they're going to self-annihilate each other, if you will, right? And so that voltage that we initially got when we initially put our tin in there, it's just going to dissipate away because we're going to cause the ions to react away together. Okay. Now, will it go completely to 0? Honestly, I don't know. I doubt it because these are still dissimilar materials. And there's probably still going to be some slight difference in voltage. But over time, you're going to find that voltage is going to go very close to 0, and you're going to get no net current. Now, you could also argue along the same lines that you can put current here too. And the current, you would initially have a current that would go do the same thing, start out and then go to 0. Okay. So that is the basis for generating electrochemical potential, is having two different redox couples, okay, two different what we call couples, okay. And let me clear that again. So let's see, anything else here?
So just quick question. So based on
Surely.
what we have in front of us, what would the voltage of that be?
All right, we're going to talk about that in a second, Connor. Okay, so hold that thought.
Okay.
But I do, we got, that's one of the essential questions of this discussion, is how do you calculate those voltages? And we're
Okay.
going to do that. We got a table that's going to really help us a lot. But before we get to that question, I wanted to bring up one other thing, and that is what if. Now, what if instead of having a single solution that we exposed our, two electrodes to, what if we did this? What if we put a membrane here or some other separator? It's called a battery separator, in fact. What if we put a separator there that allowed just our sodium nitrate to pass through? Okay, so if we had a separator there and we separated our tin couple from our silver couple, then we could not get that electron transfer between those two species, could we not? We could put a separator, and I'm just saying, again, theoretically, we can separate those two ions from each other and prevent them from mixing completely, okay? And if we do that, and you think about your voltage over time, if we do that, then we find that that voltage is very stable, okay? That, folks, is the essence of a battery. That is the essence of a battery, okay? These two reactions that are allowed to occur independently of each other because we can separate those two chambers is the essence of a battery, okay? We prevent them from mixing, so we prevent all that energy difference between those two couples from just, whacking out each other. That's the basis of a battery. This is a separator. Just remember that, okay? So far, so good? All right. Now, okay, so let's review. Energy is created when these electrons combine with oxidized species in these half reactions. I showed you that. The amount of energy varies according to the valence electron properties of the resulting species, how stable it is, which, you're going to see this manifest in a table in just a second. But this energy, so this energy associated with each half cell is referred to as the standard reduction potential, okay? So in other words, what I'm saying in a nutshell is these electrons have a certain energy here, E1, right? These electrons over here have a certain energy, E2, and that difference, delta E, is equal to, of course, E2 minus E1, let's say, minus E1, or E1 minus E2, and that is the essence of electrochemical energy, battery energy, galvanic cell energy, whatever you want to call it, okay? Galvanic cell, okay? And that's, in a nutshell, the fundamental essence of electrochemistry, is being able to manage the electrochemical different energy differences between species in these different redox couples. All right, so let me go back and move on here. What do we mean by that? All right, well, let's talk about that. All right, here's the table. Just has a lot of good stuff. I'm trying to move so I can see what I've gotten here. Got some stuff on my screen. All right. So this is a table of standard reduction potentials. Yeah, selected standard reduction potentials at 25 degrees C. Okay, does everyone see that on the top of that table? Standard reduction potentials. You will see tables like this in your many of your textbooks, okay, along with tables of other thermodynamic data, okay, because it is a thermodynamic quantity, okay. And the reason the ranking is as it is goes back to these electron energies. Now let's talk about this in a way that I think will make it clearer. Okay. Let's go to the very top of this table here. Does anyone know what that element refers to, that symbol?
Gold.
Absolutely. AU, that's one of our favorites, right? Can't get enough of it. And do you ever commonly hear about, well, you probably can readily answer this, gold 3+. I mean, you hear about copper 2+, right? I mean, copper is used, copper ion is used as a biocide, for example. It's relatively common. Of course, here's another one of our good old friends, the proton, right? You commonly hear about some of these others. Nickel 2+ is a common transition metal ion. You don't hear about gold 3+ much. Now you can make it, but one of the reasons you don't hear about gold 3+ is because, and Nathaniel just answered the question, we all know about this guy gold. It loves to be gold in the zero state. The reason it does is because gold 3+ will oxidize almost anything. If you put gold 3+ in, let's just say, I'm not getting that right there yet. Let's say we can make gold 3+, and of course you can buy it. It's rather exotic. But let's say we put gold 3+ in a solution, and I'm going to draw a line. Let's say we put it in a solution that contains sodium iodide in a I-, okay? Let's say we put our gold 3+ in that solution within a I-, okay? What do you think is going to happen? And the hint on that is, look at where iodide, the half cell, for its associated half reaction, is located relative to this guy. And keep in mind this little arrow I've got, trend in free energy. In other words, I got two things. This is even more relevant. This reaction is the most favored reaction on this table because of its high E0. Very favored delta G, so to speak, okay? So with that background, if I put gold 3 in a solution with sodium iodide I-, what do you think is going to happen?
It's going to oxidize the iodide and you'll have I2+.
You got that absolutely right. That's exactly what's going to happen. Gold 3 is going to react immediately and very quantitatively with I-, and it's going to convert I- to I2. Now, what has happened when that goes on? Well, it's all here in the table. Gold 3 has picked up 3 electrons from I-, right? So 3 electrons were pulled off of I-, and those 3 electrons were created some number of I2. Well, 1.5 I2, you'd have to quantify that, and we won't focus on that too much right here. But conceptually, This guy is what we call an oxidant, right? This guy here is called a reducing agent. I'm just going to call it RE, reductant, okay, or something like that. Reductant, reducing agent. You see it termed differently. And so the I minus is going to reduce the gold 3. Now, is everybody okay with that concept? And again, you can look at the table and look at these numbers. Which one's higher? The gold 3 is higher. So that means it has more delta G, if you will. It has more energy to oxidize, because this equation is an oxidation reaction, right? Gold 3 is oxidizing something. It's grabbing electrons. So it's oxidizing something, right? And it's going to gold 0. All right, now this is a question, and I'm be curious for someone to tell me, because this is the second big concept here. What energy is related to the oxidation of gold 3, or the oxidation, I'm sorry, of I minus by gold 3? How much energy is available given this table to do that? And I know I've not described it to you yet. I'm asking for a guess. We'll start out here. See, EOX minus E red. And where's EOX? It's right there, right? So delta E is equal to, what's that, 1.5 roughly? 1.5 volts minus 0.54, 0.54 volts. So that gives you what? A delta E is equal to 0.96?
Yeah.
Okay, good. 0.96 volts. That, my friends, is equal to our delta G. It's delta G in terms of voltage. Now, we have seen delta G, right, in the past in our thermodynamics section, and delta G is associated with typically what, like a kilojoule per mole or kilocalorie per mole. Here we have delta G in terms of a voltage. Now, I'm going to tell you, and then we're going to show you later, don't sweat that difference. You can convert a voltage to a joule per mole or a kilojoule per mole. There is a direct way to do that, and it's just a matter of knowing what the constants are to do that. So the point being, delta G is perfectly, or voltage is a perfectly legitimate manifestation of the amount of free energy. So the amount, if you will, of possible work. So a battery gives you a voltage, delta E, which is also analogous to the delta G provided by that battery, by that galvanic cell. Now, so we did a gold, what did we do? Gold iodide. If I were to say, well, let's say we want to do, let's pick one here. Let's pick, say, platinum 2+, cobalt, and I'm gonna circle my reactive species. If I gave you that as on an exam and said, tell me what the delta E is when you expose equal molar, again, we're talking about equal molar, I should have mentioned that. Equal molar amounts of platinum 2 and cobalt, metal. Will they react? That's the first question. Will platinum 2+ react with cobalt 0?
I think it should.
Absolutely will. I mean, it should. Yeah, that's probably even better answer, Nathaniel. Thermodynamically, it certainly should. Now, kinetically, we don't know really, right? I mean, it could take years, but thermodynamically, absolutely. Delta E is equal to what? 1.2 minus what? 0.28 is equal to 7.72. Is everyone getting the math that we're doing here?
Dr. Jernigan,
Yes.
on that, would you have to add it since it's negative? Or did I miss
Oh, I'm
something?
sorry. I am so sorry. Gosh, you're exactly right.
It'd
You're my
be
straight man.
1.48.
Yeah, you're my straight man because I made a mistake. So it's actually 1.48?
Yes. Of course, you could say 1.2 minus negative 0.28, which would keep it
That's
informed.
right. That's right. That's where that minus a negative gives you a plus, right? Yeah, 1.2 minus a negative 0.28 gives you a 1.2 plus 28. Does everyone see that? This is essentially basic arithmetic. And that's why, this is pretty cool. It's pretty straightforward to determine energetic relationships in an electrochemical sense because you've got these cells. Now, two things. Number one, this is admittedly these are rather simple relationships because we're not differentiating in terms of concentration. You do need to account for concentration. It has a minor effect, okay, on it, and the ACS exam or whatever exam, if I were to give you one, they might have different concentrations in there, and we'll show you how to account for that. But fundamentally, you're still just simply subtracting the two half reaction potentials in order to get to a free energy type of answer. That was point number one. The other point too, and this is a little more subtle, and you're just going to have to take it on faith. If you're looking at, let me show you this thing, and let me go back to my silver. I'm sorry, my gold. That has 3 electrons associated with it. Let's say we're going to react it with silver chloride. It only has 1 electron associated with it. So thermodynamically, voltage is considered an intensive quantity. In other words, voltage is like temperature. It doesn't care how much you have. Now, the current you get from that voltage or how long your battery lasts obviously depends upon how much material you have. But the measurement, the metric, the voltage that you would measure, like temperature, could care less. It's like temperature, it's like, what is it, a density, things of that nature. I think they refer to that as an intensive quantity. So in other words, 3 electrons versus 1 electron, when you're calculating voltage, don't worry about it. You simply just have to subtract the 2 half reactions. That makes it easy. You got to take it on faith for me. I know to me, it's a proof. You can prove it, but suffice it to say, it's like temperature. It's intensive, and don't worry about the numbers of electrons and whether or not they are different. Okay. Now
Dr.
again,
Jernigan?
yes.
Okay, so would that be kind of like where you have a dead battery, but you could put a voltmeter on it and it might still read, like if you had a AAA, 1.49 volts, and then you put a load on it and it just dies?
It doesn't have enough oomph to do anything, but there's still enough there that you can make that measurement. That's exactly right. It's exactly right. That's a good way to think about it. It simply does not tell you anything about the capacity to do things. So it is a measurement of work, but it's not a quantification of the amount of work available. Okay, if that makes sense. But yes,
Yes.
that's right. Yeah, you can still measure a voltage. In fact, you can have a dead battery and go to Advanced Auto Parts, and they'll measure a voltage on it, won't they? Often, a big voltage. It just doesn't have enough juice to convert anything. Thank you. All right, let's move forward here. We're doing okay. A couple other things here before we get into some other nitty-gritty stuff. I think we've talked about most of this. One thing that we, again, highly oxidizing species are at the top. Highly reducing species are at the bottom. And what I mean by that, again, you have to look which side of the equation are you on, right? Cobalt 2+ is theoretically an oxidizing material. It's just a very hugely weak one, right? It's almost like acid-base chemistry. Cobalt 2 is it's not going to reduce anything. The thing that has the high reducing tendency is the cobalt 0, right? Because it's going to suck those electrons away from anything. Similarly, the highly oxidizing nature is the folks on this side of the left side of the equation, right? So just remember that when I say highly reducing, I'm talking about the guys on that side of the equation. They're pulling the electrons. Okay. These guys, these guys here are the high oxidants on the left side. So it's just think about it. When you want to react something, you're gonna have to go. You got to go crosswise. You got to go from the reactant to the product. Is that clear? Got to be. So this is a subtlety. Okay, good. All right. Now, anything else? Hydrogen. Hydrogen is defined to have 0 volts, and that's really cool. And I'll tell you why that's cool. In reality, we couldn't have done any of this without having 2 electrodes. Remember, you have to have 2 electrodes in order to measure a voltage. You simply can't measure a voltage with one electrode because a voltage it's inherently a delta E measurement. And it's just a delta E measurement in your car, the delta E you measure in your flashlight battery, the delta E that you need to measure when you're doing thermodynamic electrochemistry. You still have to have 2 electrodes. Show me a battery with 1 electrode. You're going to win the Nobel Prize. It just doesn't exist. Clear enough? Let's see, anything else? I think we got this one. Let's move on to the next slide. Okay, we've already talked about this. Which side of the equation is the oxidizing species on? It's on the left side, right? Because it's grabbing the electrons. It's grabbing the electrons, just like we showed here. This guy here, grabbing the electrons. Okay, it's oxidized. It wants, it's going to oxidize something else, right? It's a high oxidant, but it actually gets reduced. Oxidants get reduced. Think about it that way. Okay, oxidants get reduced. All right, same thing through a reductant. Reductants get oxidized. The reductants is readily available, ready to give up those electrons to someone else. It doesn't really want them. It wants to be, it wants to get oxidized on a relative basis. It wants to get oxidized relative to anything above it. It wants to get oxidized. This guy here, relative to anything below it, wants to get reduced. Okay, I spent a fair amount of time on the table, but the reason I did is because there's a lot of valuable information in these tables. It really depends upon how you want to look at it, okay? Now, again, we have not talked about concentrations. We're assuming everything is kind of unit, kind of 1 molar types of things, so that we don't have to worry about concentrations. I will show you either today or the first few minutes of Monday, if you can join me, how to take care of concentration. Straightforward, but yeah, it's probably something you should be aware of. All right. I think we talked about all this. Oh, we haven't talked about one part of this though. question, can we make the electrons flow in the opposite direction? So in other words, you know, if I was taking my gold and I had connected it to a copper, and I had gold, you know, gold 3+ in my solution, right? And a gold electrode, and then a membrane, and then a copper 0 metal electrode, and I exposed it to gold. Electrons are going to flow, like we talked about, right? Theoretically, can I make the electrons go the other direction? Can I make them stop flowing? And the answer to that is, again, thermodynamically, absolutely you can. But what do you have to do? You have to apply an opposite voltage to the delta E. You have to apply a negative delta E, or really a little more than a negative delta E, to get the electrons to go the other way. Okay? And we often do that. We often apply voltage to electrodes in a solution if we want to create an electrochemistry that is not thermodynamically favored. We just simply apply a voltage the other way. We connect our power supply to a 110. That's how you charge a battery, isn't it? You just connect it up to a current. Recharge your battery. You force the reactions to go back to the way they were. You force them to reverse. You force the half cells to go in reverse. You force those half reactions to go in reverse. Charging a battery, that's the way you can think about that, okay? Battery discharges, it gives you delta G. Battery charges, you gotta get it back, right? All right, now let's see. Just talk about a little example here. So let's say we've got a 10 solution. I'm talking a 10 electrode. Actually, we can do 10. I guess we can do 10, sure. So we got 10, and we have silver. So we've got silver on one side and 10 on the other. Let's think through this. What's the half reaction? All right. What is the half reaction? That's a little hard to read. I apologize for that. But we've got a 10 metal making 10 2+, right? 10 2+ plus 2 electrons. I see it. So it's right here, isn't it? 10 2+. Yeah. All right. That's one reaction. And what did we say the other one is? It's this one's silver. Silver 0, silver plus. So that's our couple. And where is silver? Let's go up here and find it. It's almost hard to read, isn't it? But I think that's it. All right. So does everyone agree that those would be the two half reactions?
Yes.
Awesome. Great. All right. So those are the two half reactions. Now, which one is going to be doing, if I've got silver, I've got silver ion. Yep, sure enough, got silver ion. And this one here is 10 SN2+. Got both couples there. Which one is going to be doing the oxidizing?
AG.
Exactly right. That's exactly right. It's AG plus 1 electron is going to AG0, right? All right. And then I'm gonna do something. It's a little confusing, I think, but I apologize for that. But I think it may, in the end of the day, it's going to make more sense. I'm going to reverse the 10 half reaction, and I'm going to say SN is going to what? SN2+ plus 2 electrons. So in essence, I put this is E1 and this is E2. Delta E is equal to E1 minus E2. Fair enough. I always like to put my oxidant there if it's a galvanic cell, because delta E needs to be positive if it's a galvanic cell. If it's not a galvanic cell, or if I had to apply voltage to charge my battery, delta E would be negative because I'd be applying it. It'd be costing me energy. But delta E is positive, and I'm going to show you the delta E delta G relationship in a minute. There's a sign effect, but it'll become clear. So let's just assume delta E is positive. We want it that way. And so E1 minus E2. Now if I take E2 as written, it's 10 2 plus 2 electrons going to 10 0. But do you see that by me putting a minus sign there, I just flipped that equation, and so now I have 10 going to 10 2 plus 2 electrons. Okay, and now just like we've done in all of our thermodynamic work, you can add those two babies together. Silver plus 10 is going to what? Silver 0 plus 10 2 plus. Okay. All I did is, I just don't have a lot of real estate to work on here, but this is what we're essentially doing. We're taking silver plus, we're acting it with 10, SN, we're going to silver 0, and we're making 10 2 plus. Now we're half the way there. There's an issue here, and I want to share it with you. Anybody want to hazard a guess what that is? Now, again, it doesn't make any effect on our delta E, but we really do need to balance this equation. And here's a problem. That has a +1 sign, that's got a +2 sign. We need to balance that, don't we? How would we do that? Well, you think about it. I'm gonna
two silver.
That's right, you're on it. That's all you'd have to do in this case. You just give yourself another silver. So it's 2 silvers here. And of course you got to put 2 there. Are the charges now balanced? Absolutely. Is the stoichiometry right? It's a fully balanced equation. Both the stoichiometry and the charges are balanced. Now, we're not going to talk about balanced charges today. That's one I want to try to do Monday, and of course I'll record that. I'm going to give you a couple of problems, again, optional problems in sapling to let you do some balancing. They can get pretty hairy, but again, you'll have a little experience with it as part of the electrochemistry chapter. So that's got that.
Jernigan.
Yes, sir.
So again, like you said, now that we have 2 silver ions, it does not change the voltage associated with that.
No,
but
not at all.
If we were to take and make, let's say, 2 cells a piece on either side and then hook them to the wire, then you would be changing the voltage, correct?
Okay, now are you talking about so that you increase the voltage?
Yes, like in other words,
Yeah.
if you had 2 of those beakers there, hooked to the same wire on each side going across, then it would be like a series situation.
So voltage is V is additive in series, because you would add them in that case, right?
Yes.
I'm pretty sure you would. So yes, that's a good point. So in other words, if you have a battery like that, I think this might be where you're going, and then you gang them up so that you make your negative here, you connect it to a positive. Is that the way that works?
Yes, that would be a series voltage additive.
And you put them in series. That's in series, right? So then the sum of the voltages is equal to V1 plus V2. That's absolutely right. And yeah, that's right. That's right.
But as long as you, like in this situation where you just have the two, the positive and the negative cell basically, then it does not matter how many of the species you have if it's just one going to one.
That's exactly right. And
Okay.
it just simply does not matter at all. So you don't have to worry about that when you're doing delta E. But yes, there are, of course, if you need more voltage, you gotta put them together in series. But that is getting away from the actual thermodynamic chemistry and more into the engineering side of it, right? You're now,
Okay, yeah.
yeah, you're designing, you're engineering, and using using the constructs in more of a macro way. But absolutely, I would agree with that. Okay. Another one, we don't really need to talk about this too much. I think I showed you already. This is a copper example, and silver, copper, silver. And again, look here, where's copper? There's copper. All right, there's copper. All right. And silver here, where's silver? Oh, there's silver, okay. All right. So yeah, silver plus and that's what they did. Silver plus electron on the silver zero, and then they essentially subtracted the copper, right? And they got that. They got that. And then they added the two together. That's all they did. Same thing we did. Once you get this, you got it. You can make it happen. Now, a cool thing here, we talked a little bit about a membrane. These guys are not using a membrane, but they're using, in principle, the same concept. And that concept allows you to actually separate your two cells. You completely two different cells, and they're conjoined electrically. They're electrically joined by this salt bridge, but they are spatially separated because, again, you don't want those guys to mix together. They're just going to react away, and you'll lose your oomph. Okay. But salt bridges are also membranes. One of the students yesterday mentioned osmotic membranes, and an osmotic membrane is a very good membrane for separating charged species. You just got to get the sign of the charge in the membrane right, so that you do the right separation. But you can absolutely use different things as long as you keep the species from commingling. Okay. Need to keep the species from commingling. All right. And of course, they calculated 0.46 volts. Let's do that. Copper, we'll do it real quick. My silver was 0.7996, and the copper, let's see, where's the copper here? 0.34, so 0.79 minus 0.34, so 0.8 minus 0.34 is about 0.4, yeah, 0.46, that's about right, isn't it? That's what they came up with. All right, so that works. All right, let's move on here. We're going to run a little bit short on time, but I talked about this, and this is just the words around it. Potentials are like density and temperature. They're independent of the quantity of the material present. This is a key thing to know for you guys. This is different from Hess's law calculations and other calculations of thermodynamic quantities, such as enthalpy, entropy, and free energy. You remember Hess's law, right? The sum of the delta G's or the delta S's or the delta H's of the products multiplied by the stoichiometric coefficients. You take the sum of the products minus the sum of the reactants, right? Well, the coefficient goes in Hess's law. It does not go into our calculation for delta E. Okay, when you go, and we'll show you in just a second, we got a little bit of minute here. When we do that delta G conversion, you'll see where it comes out, I think. All right, let's go on and move, go next. Okay, we've done this. Okay, this is probably where we're going to have to end today, but I did want to show you. It's the same example we looked at before, and I want to give you about 3 concepts that I want you to you know, leave my class knowing, okay, if nothing else. One is we've talked about some of these other ones, but these are the additional 3. One is current, okay, amps, coulombs per second. All right, and again, every time you get copper, and just I'm taking this for example, every time copper goes into solution, how many electrons are going to go out to the other side? For every copper atom that goes in, how many electrons do we get?
2.
Absolutely right. You get 2 electrons. So, and then for silver, you get 1. Okay, but this reality, if we count those electrons, if we put an electron counter here, let's put I for an ammeter. That's an electron counter, isn't it? An ammeter. You current times the time equals coulombs, because current is coulombs per second. Current's coulombs per second. So coulombs per second times time equals coulombs. Okay. And let's see, anything else here? So if you, yeah, and if you, so a coulomb that you measure is quantitatively related to the chemistry that's going on in your solution, quantitatively. And that's the basic of some analytical chemistry techniques. Is one is called coulometry. Okay, now so we get a voltage, right? That gives us the thermodynamic. The current gives us the ability to quantify the chemistry, to actually quantify it. We do that by counting coulombs or measuring current over time and multiplying by time, right? That gives us coulombs. And now the final piece of this is, I'm going to circle it right down here, is you actually can convert those coulombs into moles of substance, okay? So Q is equal to N M F, okay? N, all N is N is the number of electrons, okay? N is the number of electrons, okay? M is moles, so all it is moles, is straight moles. And then F is a constant. Mr. Faraday, thank goodness, he figured it out for us, how many moles I can get for my coulombs. So he gave us this conversion factor, if you will, to get from coulombs to moles. F is equal to 96,480 some, 485 here in this example, 96,485 coulombs per mole. All right, so let's just do a quick example. I think I have one on the next page. Let me clear that. And then go on to the next page. No, I think we're going to run out of time. All right, anyway, so if, let's just say if Q, let's say Q is equal to, say we passed 100 amps, 100 amps. And it took an hour, 1 hour. How many coulombs is that? 100 coulombs per second, right? Times, let's convert an hour to second. That's 3,600, isn't it? 3,600 seconds. So 3,600 times 100 is what? 36.
360,000.
Okay, it's 360,000 coulombs. All right, that's how many coulombs we passed. All right, in 1 minute. So let's get rid of that. Let's use this equation here. So 360,000 coulombs, 360,000 divided by, and let's look at our copper example, it's going to be, we're going to have to divide by 2, right? The 2 is in, 2 electrons times F times what, 96,487. And again, I'm not able to put the units. You should do that to keep up with them. But this is coulombs per second. I'm sorry, coulombs per mole is the Faraday, right? So coulombs per mole, got coulombs on top, and that's going to give you, can someone calculate that for me? 360,000 divided by the quantity of 2 times 96,487.
It was like 1.866.
So let's just say 1.9. And what are the units? Moles of copper. So we plated out 1.6 moles of copper in that amount of time, okay? In fact, I think it's the other way around. I think we actually dissolved that many moles of copper. It depends on which way yeah, we're dissolving copper, right? We're going, because it's lower in the table. Does everyone see that calculation? It's a way to get from current to numbers of moles of this electroactive species. And this Q is equal to N times M times F. All right, folks. That's it for today. We're out of time. Look, we will finish up Monday. We're going to finish up on this section. We're going to talk about the Nernst equation, tie delta G together, and to that, and do some, show you how to get concentration out of it. And then we'll be finished up. Take a look at the that sheet I showed you, or I sent out from, it was from Dr. Pearson, and that's the sheet that you will have available to you